Module 7, organic chemistry. A fair bit to get through, but we'll make our way through it all. Just to recap, the structure for every single, well, for Module 7, the structure is that you learn structures, you learn how to name them, then you learn for each structure the properties, the reactions of how they're made, the reactions of how they convert into other things, and how you can use that substance in a real life application. So it's sort of this blue box. You repeat it for every single structure that you learn, and that's the flow of the module. So starting out, we learned how to name organic compounds. We talked about how carbon can have single, double, or triple bonds. And now we know that every single covalent bond is a shared pair of electrons. So if you have a single bond, it's 2 electrons. If you have a double bond, it's 4. And a triple bond is 6. We were able to draw organic molecules in structural, condensed, and skeletal forms. In your exams, please draw structural for every organic molecule you draw. It's just safer and it cuts out mistakes, and it's also safer in terms of what markers
Okay,
actually mark correct.
are you gonna put the notes in the chat, or is it the
Uh,
same notes that we already have?
am I sharing my screen?
Yeah, you are.
Yeah, these should be the same ones, but I'll put them in the chat as well.
Oh, yes.
Okay, so they're just sending, but it's a big file, so it might take a moment. Okay, I'll get going again. So for the structures, as I was saying, structural formula is always best, where you show all the bonds between atoms uh, as lines. So even if it's a hydrogen to carbon bond, you show the whole thing. Okay. Keywords: substituent, side chain, and functional group. A substituent is any additional group of atoms that's added onto the carbon chain that replace a hydrogen. Side chain is all of your methyl groups, like your alkyl rather. Your alkyl groups are methyl, ethyl, propyl, so on and so forth. They are all side chains, which are branches of carbons that come off the main chain. Functional group is any group of atoms that give a characteristic uh, reaction, like chemical property, that the ability to react in a certain way. So bromine, hydroxyl, or a carbon-carbon double bond are functional groups, hence function allows them to do things. Homologous series is where you have um, a molecule that differs from another by just a CH2 group. And every member in that homologous series is just going to be different when a CH2 is added onto that chain. Otherwise, the part of the molecule that originated, so for example, methanol, you've added on a CH2 into the chain. Otherwise, the rest of the molecule stays the same, where the OH is right on the end of the chain. You're adding a CH2, OH still on the end of the chain, add a CH2, OH still on the end of the chain, and it goes on and on. Locants describe where on the chain a functional group is. So 2 would indicate it's on the second carbon, and you always want to number the molecule lowest to have the highest priority functional group assigned the lowest possible locant. This page takes you through how to name a complex molecule. Prefixes, make sure these are memorized. The priorities of functional groups, these aren't really too important because for the most part, you only see one functional group per molecule in HSC. But having a general idea of the hierarchy is not a bad thing. So knowing carboxylic acid, ester, amide are really high up. Then you have aldehyde ketone, then alcohol, amine, alkene, alkyne, alkane, and below. I think one important rule to just remember is if you have a functional group present, the main chain has to include it. So this molecule, the longest chain is 7 carbons going across this way. And so it would make you think this is going to be a heptane chain. But whenever you have a functional group present, such as this OH, the main chain must include that functional group. So this is actually the best main chain, which has 6 carbons, and that's the longest chain that contains the functional group. And it would be more correct to name this molecule with the functional group as part of the parent chain. Okay. Then whenever you have more than one of the same substituent or the same functional group, you include a separate set of prefixes in front of that, di, tri, tetra, penta, to describe how many of that substituent or functional group you have. Side chains and alkyl halides come at the front of the main chain, and typically the functional group goes behind the main chain. And in terms of your punctuation, locants of each substituent are in front of whatever they're describing, and they're separated by a hyphen. So if you have a locant, let's just say the locant is I'll represent locant as a hash. Locant to word, you separate by hyphen. Locant to locant is separated by a comma. And if you have 2 words, 2 names, you have no punctuation between them at all. It just flows on. Okay. Any questions there on naming? Okay. So all of the functional groups that you should know, alkane, alkene, alkyne, you should know their general formulae differing by 2 hydrogens each. We should know that they have single, double, and triple bonds respectively, and that alkanes are saturated whilst the other 2 are unsaturated. For alkyl groups, we should recognize that these are your side chains, carbon chains coming off of the parent chain, and they all essentially differ by the number of carbons, and they follow the same naming prefixes. So meth, eth, prop, but. Cyclic structures, cycloalkane, cycloalkene, cycloalkynes. For a cycloalkane, it has the general formula of CnH2n, and you can derive the cycloalkene and alkyne formulas from that. But they're essentially the same as a alkane in the case of cycloalkanes, just that the chain is not not joined together on either side. The ends are joined together in a ring. Don't really need benzene, phenyl, and benzyl, but you should be able to recognize a benzene ring. A benzene ring can be represented as either in skeletal formula like this, or as a hexagon with a circle inside, but they both mean the same thing. It means alternating double bonds going around, alternating with single bonds, and you have a structure which has 1 hydrogen coming off each carbon. Halogenated organic compounds, alkyl halides, haloalkanes. Basically, the prefix is halo, so bromo, chloro, fluoro, iodo. Be able to place those in front. Alcohols have a hydroxyl group, so nothing too crazy here. Be able to separate primary, secondary, and tertiary alcohols. Primary alcohol having only 1 carbon attached to the carbon attached to the hydroxyl, secondary having 2, and tertiary having 3. Aldehydes and ketones, know the difference is that an aldehyde has carbonyl on the end of the chain terminally, and a ketone is in the middle of the chain, non-terminally. Carboxylic acid has a carbonyl and a hydroxyl, always terminal, and the suffix is oic acid. Amines are a bit harder to name, so probably this is where you want to brush up before your exam. You have primary, secondary, and tertiary amines, where it's a slightly different system to primary, secondary, tertiary alcohol. Primary amine has only one carbon attached to the nitrogen. Secondary amine has two carbons attached to the nitrogen. And tertiary amine has all three bonding locations bonded to a carbon. So keep those in mind for how you class amines. I think that came up in mock exam 4. To name a primary amine is quite straightforward. The suffix is just amine and you name it as pretty much any other functional group. But where people mess up is secondary and tertiary amines. So these are all, on the left is all primary amines. On the right is also all primary amines. But these are the ones that people trip up on a bit more. So can everyone have a go trying to name, let's try to name this one. Type your answers in the chat. What's the name of that molecule? As in, how would you name it, the IUPAC name? Ten seconds. 9, 8, 7, 6. Got the right ideas, Lily, but all, not quite. Got the right ideas there. Okay. So the rules for naming a secondary amine, you pick the longest chain as your parent chain. 1, 2, 3. So we know it's going to be a propane chain as our main chain. And we have an amine bonded onto that main chain. So we then refer to it as propan amine. And in this case, it's bonded onto propan 1 amine because it's bonded onto the first carbon on that propane chain. And then on that amine, you have two methyl groups that you have to name as well. And the locant we use to classify, well, the locant we use when we have carbons coming off of nitrogen in an amine is N. And we actually have two methyl groups. So it's a dimethyl propan 1 amine, dimethyl propan 1 amine with N as its locant. So we need to provide two locants to classify each carbon. So this would be NN dimethyl propan 1 amine. So if that was a little bit challenging, maybe have a go at a few more of these on this page. And the notes, I think, are just about through in the chat. Yeah, they've come through now. Any questions there? Secondary, tertiary amines? Okay, let's continue on. Amides. Suffix is amide. It has a amine and a carbonyl. Name it similarly to a carboxylic acid. Esters. You should know that the ethyl originates from the alcohol, whilst the methanoate originates from the carb acid. And you name it as such. I think actually just coming back to the amides, the only slight difference in rules is for an amide, the parent chain is independent of which the parent chain doesn't have to be the longest chain. It just depends where the carbonyl is. So say, for example, you had I think I always use this one. Say that this carbon chain was actually a bit longer. For this molecule, the parent chain would still be the chain that contains this carbonyl. That's the main chain. So this would be propanamide with something coming off. Excuse me. This would be propanamide. And it has a 1, 2, 3, 4, 5 carbon long side chain coming off the amine. So this would be N-pentyl propanamide. And since the amide is always terminal, you don't have to put a locant. Okay, cool. Isomers, remember that you have chain, position, and function group isomers. Be able to differentiate those three. Chain isomer, the chain length actually changes. Position isomer, function groups or substituents move to a different place on the same length chain. And function group isomers, the function group is completely different, whether that's changing from an aldehyde to a ketone, or a carboxylic acid to a ester, or the last one that's common is an alkane to a an alkene to a cycloalkane. So keep those in mind as common function group isomers that you typically will see. Okay. You should be able to draw hydrocarbons where you have any hydrocarbon. You should be able to draw the structural formula. Hydrocarbon shapes. It's all dependent on the number of bonds and the number of lone pairs. So you should be familiar with three base geometries and how they're all derived from VSEPR theory. VSEPR theory states that electrons in bonds will repel each other as far away as possible. And this is where you derive your linear, trig planar, and tetrahedral structures from. So these are your base geometries where you have either 2, 3, or 4 bonding pairs or bonding groups. You then have 3 other geometries derived from these base geometries, where if you were to replace one of those bonding groups with a lone pair, now all of a sudden the other bonds are splayed downwards at a similar angle. And this is our bent structure in the case of trigonal planar. Or for tetrahedral, if you replace one lone pair, that lone pair is able to deflect everything else downwards slightly to create a tripod, and that's your trigonal pyramidal. Or if you replace one more of those electrons, now you have a bent structure with 2 electrons repelling these 2 bonds downwards, like so. Okay, so you should be able to look at a molecule like this and identify the geometry around every single one of these atoms, saying either it's linear, or it's trig planar, tetrahedral, trig pyramidal, whatever it might be. Be particularly aware in your exam of oxygens and nitrogens if they ask you to do this. Oxygen will always have 2 lone pairs, whilst nitrogen will have 1. And these molecules will have the following bonding patterns. So for nitrogen, what would be the geometry around a nitrogen like this, with one nitrogen in the middle, and then say it's got it's bond to these things. What's the geometry around the nitrogen I've drawn? Type in chat or shout out.
Is it trigonal planar?
Almost.
Wouldn't it be tetrahedral?
It will be tetrahedral in electron group geometry, but I want the molecular geometry. How's that different?
Oh, is it pyramidal?
Good. Trigonal pyramidal, if you're asking for molecular geometry. And the reason why it's not trigonal planar, to be very clear, is because we have this lone pair, which you cannot forget for nitrogen geometry. And for oxygen geometry, the two lone pairs mean it's pretty much always going to be a bent shape around oxygen. Okay. Cool. Homologous series, as we said, they all differ by CH2. So be able to identify homologous series and talk about the properties throughout a homologous series and how they change. The most important properties are your boiling point and melting point, solubility, and reactivity. Remember that there's intramolecular forces, covalent, ionic, and metallic bonding. Covalent is pretty much the only intramolecular force we worry about in Mod 7. And you should be able to differentiate dispersion, dipole, and hydrogen bonding. Dispersion forms in everything. Dipole, and below only forms in polar molecules. There's two things that make a molecule polar. You need to have an electronegativity difference in at least one bond greater than 0.4. That creates a polar covalent bond. And there needs to be asymmetry, or the molecule needs to be unsymmetrical in order for the dipoles to be in order for the dipole to actually be significant on one side of the molecule.
What do you mean by the 0.4?
Yeah. So on the Pauling scale, which is how we measure electronegativity, every atom is assigned an electronegativity value. So for example, hydrogen has a value of 2.2, whereas oxygen, I believe, has a value of about 3.44. So the difference in electronegativity is about 1.24. And if you have a higher electronegativity number, it means if you were to bond these atoms together, the electronegativity of the oxygen would pull electrons in towards itself, meaning electrons exist more around the oxygen than the hydrogen, which is why oxygen tends to gain a negative dipole, whilst hydrogen gains a positive one. Does that make sense?
Yeah, thanks.
Cool. Any questions on the intermolecular forces themselves? Any of them not make sense? Okay. So just understanding for each of them, you're essentially creating oppositely charged dipoles, and a dipole is a partial charge. So that opposite charge attraction, that is an electrostatic attraction which holds molecules together, acts between them. So quick description of them all here. Dispersion, dipole, hydrogen bonding, ion dipole. You should be able to draw diagrams of each of these if you wanted to in your exam.
I just have a quick question.
Yes.
This might be silly, but like, what's the difference between like ion dipole and dipole?
Great question. So dipole is where you have the attraction between two partially charged atoms within covalent molecules. So as we just saw, or as we can see here, partial charge on the chlorine, partial charge on the hydrogen because of the electronegativity difference. Chlorine is pulling in electrons towards itself, fluorine is pulling in electrons. So that means when these oppositely charged partial charges interact, they'll attract each other. So that's a dipole attraction. Does that make sense first?
Yeah.
So then an ion dipole is what we see in module 5 in all of our ionic dissolution. It's where you actually have you do have a dipole on certain molecules such as water because of, once again, electronegativity difference of the oxygen, which pulls in electrons towards itself, and that creates positive dipoles as well as negative dipoles. But these partial charges can interact with ions, which have a complete charge, not just the partial charge. And that attraction between positive and negative, once again, creates this dipole to ion interaction, which is therefore a ion dipole. And that's stronger than dipole because you have a complete charge on your chloride or sodium in the middle. So this appears mostly in ionic dissolution. It also comes up in your action of soaps because for example, carboxylate is an ion. It will form some ion dipole with water, but mostly hydrogen bonding. Does that make a bit more sense?
Yeah, it's perfect. Thank you.
Great. And so that explains our hierarchy. Dispersion goes up to dipole-dipole. H bonding is just particularly strong dipole-dipole. And ion dipole is strongest because it has a complete charge rather than just partial charges. Okay. So then as you go up a homologous series, your boiling point and melting point will increase because as you add more atoms on to your chain, you are increasing the number of electrons, which increases the potential to form temporary dipoles. Temporary dipoles, which increases your dispersion force, which increases energy required to break.
Wait, could you just repeat that for a second?
Yes. So as you increase the chain length in a homologous series, so you're adding on CH2s one by one, that will mean that each time you add on a CH2, you have an extra 14 electrons in your molecule. And having more electrons permits stronger temporary dipoles to form. Does that make sense first, Jay?
Yeah.
And if you have stronger temporary dipoles, it means your dispersion forces between molecules will be stronger, and you'll be able to form, and you require more energy to break apart those interactions. So that leads to an increase in your boiling point and melting point. That's how you explain the first trend in a homologous series.
Okay, thank you.
And solubility in water. General rule is like dissolves like, as we've said, but for the rule in a homologous series is as you add on more CH2, CH2 is a non-polar part of the molecule where carbon hydrogen is non-polar, carbon to carbon bonds are non-polar. So you're increasing the non-polar portion of molecule, which will decrease solubility in water or polar solvents, or vice versa, it will increase solubility in a non-polar solvent. That's if the molecule is polar to begin with, but yeah. Okay. Cool. So you can see those trends here. As you increase chain length, boiling point increases and melting point increases, and therefore the state at some point changes from gas to liquid. It's important to remember that for alkanes, the state change happens between butane and pentane, where pentane is a liquid, but everything is smaller than it is a gas. And that makes good sense because pentane's boiling point is now above room temperature at 36.1-ish.
Wait, why does the melting point increase from the smaller carbons initially?
You mean why does it slightly decrease?
Sorry, yeah, decrease.
Yeah. So it's because of stacking. In reality, you can think of methane molecules as like small balls, and it's very hard to stack together balls. But once you start to get into like lines, you can actually stack together lines a bit more efficiently than balls that take up their own bit of space. So there's a stacking effect from methane to I would say butane, where you're able to stack them more efficiently. And hang on, no, that doesn't make sense. Stack them less efficiently?
So then how will the boiling point also increase while the melting point decreases?
It's a good question. Let me just clear this. So for everyone, the point that is in contention is this point here, where methane actually decreases boiling point to ethane and decrease the propane. I'm not 100% sure anymore now that I think about it again. But I'd presume that it's because of something to do with the stacking effect, maybe in the opposite way to what I just explained. But I'm not certain. I'd probably have to look that up after. It's a good question. I doubt they'd ask it on those three melting points though.
Okay.
And typically they do ask boiling point for the most part.
Yep.
Okay. Then you can also see enthalpy of combustion increases as you increase chain length. And they're the main trends that you observe. Okay. Should be able to explain boiling point, or should we explain the properties of an alkane, explain their solubility in a non-polar solvent because they are able to form dispersion forces, and their insolubility in polar solvents because they cannot form the same strength of bond. So it's not an energetically favorable process to dissolve in a polar solvent. For an alkene, the properties are quite similar. You should be able to explain the same thing, that boiling point increases as you increase chain length. And similar for solubility. The chemical properties are that alkanes are unreactive, they can combust, and they can react with halogens to make chlorine gas and bromine water. And this all comes back as we do our flow chart. Chemical properties of alkenes, there's a few more, and again, we'll revisit this when we look at the reactions. There's a few other factors that affect intermolecular force apart from just chain length. So yes, the chain length matters. The longer the chain, the more intermolecular force you have from dispersion force. But also other factors that are important are the ability to stack in a compact crystalline structure. So if you have linear molecules that stack together well, they will have higher dispersion force than similar molecular mass molecules that have significant branching. Position and access. So if you have a functional group that exists on a molecule, if it's easier to access on the end of the chain, it will have a higher melting and boiling point compared to a molecule which has a similar function group, but is on a harder to access part of the chain, such as being on the middle. And the function group trends of boiling points from the bottom to the top, I would pretty much say this is the way it goes the whole way. The middle region with ketones, aldehydes, esters, and haloalkanes, it's very hard to know actually. So I would just say this is all like similar. It really just depends. And you can't know very well for the orange line, but you can justify the differences in the red hydrogen bond forming molecules, and you can justify the green hydrocarbons in a simplified way where you just say, if you have more hydrogens, there'll be more dispersion force. And so the alkanes will be higher than the alkenes, and the alkenes will be higher than the alkynes. This is not how it is in reality, but for HSC, this is how you justify it. These diagrams are essential. You need to be able to draw hydrogen bond diagrams for amines, alcohols, carboxylic acids, and amides, and be able to justify from bottom up why the boiling points increase one by one. So amines have the lowest because they cannot form, well, they only form one H bond per molecule. Alcohols are slightly higher because they also only form one H bond per molecule, but the bonds are slightly more polar because oxygen is more electronegative than nitrogen. Carboxylic acids, same, only one hydrogen bond per molecule, but they form dimers. And dimers are arranged sort of like two carboxylic acids interlocked, and they have relatively high dispersion force because they pack the molecules tighter together. You can also think of this, some schools also teach that it makes the hydrogen bonds stronger because the dipoles are slightly strengthened. That's also true. So whatever your school's taught, or if you want to take my reasoning, they're both correct. And lastly, amides form two H bonds per molecule, which means they have the highest boiling point by far. So know the reasoning going up, be able to draw diagrams to justify what you're saying. And finally, know that like dissolves like, and when you are dissolving in water, you don't necessarily need to have OH in order to form a hydrogen bond of water, because water can provide positive dipoles. So a carbonyl can actually form hydrogen bonding with water because it has a lone pair that it can offer to bond with water's positive dipole. you should be able to justify how you handle and dispose of organic substances. There's a few rules here. Talk about the implications of hydrocarbon extraction as well as use. So there's some advantages, disadvantages here. Feel free to take these. Okay. Crashing through the reaction pathways. Everything's here that you need to know on this pathway. So we'll just go through the flowchart. We'll start at alkanes. You can form an alkane from, well, you can react to alkane in only one way, which is reacting with a halogen and doing a substitution with UV light. That makes a haloalkane. You can also do cracking of alkanes, although this is in the syllabus. If they tell you something about cracking, it basically means that you're breaking an alkane into two smaller pieces, where either you have two smaller alkanes or you have an alkene and an alkane. The one where you just have two alkanes is called catalytic cracking, and thermal cracking with high temperature forms an alkane and an alkene. So that's the only way you can go from an alkane to an alkene, through thermal cracking. Then looking at alkenes, maybe we'll just highlight what we've talked about, just so we move through. Looking at alkenes, you can do hydrogenation, which is hydrogen PD on C. You can do hydrohalogenation with a hydrohalogen, halogenation, and you can do hydration with dilute H2SO4 to make alcohol. Okay, with alkynes, you can turn into alkenes. If you want to stop it at an alkene, you have to use Lindlar catalyst, which is actually just contains PD on C. So if you said H2 and Lindlar catalyst, that implies you have the PD and palladium on carbon in there already. So that allows you to form alkenes. And if you were to hydrohalogenate or halogenate a alkyne, you would make polyhaloalkanes along the way. Okay. Then for alcohols, you have a few reactions as well. You can do, first of all, fermentation with an anaerobic environment, Zymaze in 37 degrees Celsius to make your alcohol in the first place, so ethanol. Depending on what alcohol you have, you can do some specific oxidations. So primary alcohol turns to an aldehyde with water, and then if you oxidize that again, it makes carboxylic acid. One step that's not included in this flowchart that I should have included is if you want to just make an aldehyde and not go to a carboxylic acid, you use a weaker oxidizing agent such as PCC, and PCC stops primary alcohol oxidation just at the aldehyde. So remember that case. That's probably an important one. Secondary alcohols, they make ketone and water, and tertiary alcohols, they do not react when oxidized. You can dehydrate an alcohol using concentrated H2SO4, and you also need heat here. Then you can substitute the alcohol hydroxyl group with a hydrohalogen in order to make a haloalkane. And lastly, you can combust alcohol either through complete or incomplete combustion. Same with alkenes, alkanes, alkynes. And depending on whether it's incomplete or complete combustion, which are classified by either insufficient or excess oxygen, you will make carbon, carbon monoxide, and or carbon dioxide, as well as water. And that's purely dependent on the oxygen conditions. Final thing is your organic acid and base reactions. So you can make an amine from alcohol with NH3, but this isn't syllabus strictly. And then in order to make an amide, you need DCC with heat and reflux when you react an amine and carboxylic acid. And in doing so, you also spit out a water because it's a condensation reaction. And then if you wanted to make an ester, that's the reaction between an alcohol and a carboxylic acid with concentrated sulfuric acid and heat under reflux to make ester and water. So those are all the reactions. Quickly recap. Oh, there's one more. If you want to turn a haloalkane into an alcohol, you can use heat and NaOH, and that rounds everything out, I believe. Any questions on any of the reactions? All right. That takes us through pretty much all of this. Alcohol properties, you're able to talk about how it can form hydrogen bonds. Similar discussion for the trends. As it increases in molar mass, it'll increase in boiling point. But the important feature that you have to describe for polar molecules is as you increase the number of carbons in the homologous series, the boiling point does not rise as fast as alkanes. And in fact, it starts to converge with the alkane line. And you justify this as the chain length of the alcohol increases, the proportion of the molecule which is polar, OH, it diminishes while the proportion of the molecule which is non-polar increases. So you're approaching becoming non-polar as a molecule, and so it approaches the boiling point of a non-polar molecule over time. Okay. Some small difference between primary, secondary, and tertiary alcohol. So primary alcohols have the highest boiling point because they have the best access, whereas secondary has a little bit worse and tertiary has the worst of the three. Taking into account as well, if you have a branch on butane 1-ol, even though you would have higher dispersion force when compared to butane 1-ol without the branch, the boiling point becomes slightly lower because of the branching effect. So just keep in mind, access and branching are two important things to consider for boiling point. Solubility, as the alcohol becomes longer in the chain length, it becomes more nonpolar and hence solubility in water will decrease. My advice, as always, describe the trend you see on any figures you're provided or tables, explain each trend individually, and then you can compare them against one another. Best practice is you always start from, if you have multiple molecules to compare, you always start from the lowest boiling point or the lowest strength in terms of intermolecular force, because it allows you to build each molecule on top of that, rather than giving everything and trying to cut back each time. That wastes words. The most efficient way to answer is you start with the molecules that have the lowest intermolecular force, add the next one, add the next one. Always include diagrams, and that's pretty much all I have to say here. We've gone through these reactions. We've gone through these reactions too. So for oxidation, you should know about the color changes as well, and that the color change comes from the change in color of the oxidizing agent. There's another way.
For the diagrams, when you're answering trend questions, what kind of diagrams could you like include?
Yeah, so you can include either dispersion force diagram, which is really simple. You just draw like a line between two molecules and say dispersion force. You can include a dipole-dipole diagram where you show the polar group and you're showing an interaction between the positive and negative dipole. So let's say you had a carbonyl. You had a aldehyde, and you want to show negative, positive, that it interacts with another carbonyl. Like this, you would draw a dotted line between them, and now this is a dipole-dipole interaction. So if you want to show that, you can. And then the most common one that you're going to need to draw is a hydrogen bond diagram between alcohols, between carboxylic acid, between amines, between amides. That's your most common diagram you're probably going to be drawing. And the only other one I can think of is if you're trying to describe solubility, showing how a molecule can form hydrogen bonding with water is probably the last one that I think of.
Isn't that like the hydration sphere?
Not necessarily for mod 7, because hydration sphere is for mod 5 when you're dissolving an ionic compound and you're forming ion dipoles. But for a organic molecule, going back up to here, these are all the possible diagrams you draw for things that could be soluble in water. So here you have your carb acid, you have aldehyde, you have amine, ester, you have an amide, ketone, and then hydroxyl. So this is showing where water can bond onto each of these molecules, and you draw it like that.
Okay. Yeah, that makes sense.
Okay, cool. All right, we're just on the oxidation going back to where we were. So I was just saying, be familiar with the color changes. Know that dichromate goes from orange to green. Know that permanganate goes from purple to colorless. You can potentially stop a oxidation using distillation to remove the aldehyde as you make it. So you can either do this or you can use PCC as your oxidizing agent. Okay. Enthalpy of combustion. So you should know the two main equations, sorry, that you have Q equals MC delta T, and there's a typo on this. This should be delta H of combustion, and the definition is slightly different. It is not the energy released per mole of water, it's the energy released per mole of fuel. Okay. Always match your units. So you're always matching to your C. If you use joules per kilogram per Kelvin, everything else has to be in those units. Quick description of the prac and some factors that can affect the delta H, which cause error in your experiment. So you should be able to discuss these as you go along. Cool, we've talked about these as well. Production, fermentation, quick summary of the reactions and pathways to practice. Biofuels. So you should have a response prepared for comparing and contrasting fuels from organic sources to biofuels. Something prepared there already. Organic acids and base. To summarize this entire inquiry question, it's basically just being able to identify that you have carboxylic acids, which are acidic, and your bases include amines. Everything else is pretty much within those two and are virtually neutral. So even amides are pretty much neutral, and aldehydes, ketones, alcohols are all neutral as well. Same discussions, boiling points, and here's the diagram for dipole-dipole reference again, Jay, if that's unclear still. Amines, amides, revising the naming, physical properties. Same kind of discussion with boiling point and solubility with alcohols. I guess the only thing to consider for amines and amides is to be aware of tertiary amines. If you have a tertiary amine, C, N, C, C, you'd actually find that there's no possibility to form hydrogen bonding. So a tertiary amine is actually a non-hydrogen bond forming molecule. Just be wary of that. Amides always form hydrogen bonds because they have lots of bonding sites. Even in a tertiary amide, you can still form hydrogen bonding. Carboxylic acids, be able to draw the dimer diagram, describe hydrogen bonds and the increased dispersion force or increased strength of hydrogen bonding, and they are very soluble too. So coming back to our hierarchy, having discussed them once again, you should have the hierarchy going from bottom to top and be able to group molecules as those that can form hydrogen bonds, those that can form dipole-dipole, and those that can form only dispersion. And that will allow you to navigate any response where they're asking you to justify the boiling points. And once again, differentiating each of these this comes up again because it's just so important. This is a sample response for how I would go about things. So as I was saying, if you would explain the boiling points of these three molecules, I would start from lowest to highest if I had the choice, because it means that I can start with just a small bit of text describing pentane very simply. Then I can add on top a bit more text for butanol. And finally, I can add on all the detail I need for butanol, which compares against the previous two molecules. But if you start with butanol, you have to repeat yourself on all of this detail in butanol through each of these paragraphs. And your response would end up being like 4 of these chunks, which is longer. Small things, but it does save a bit of time. And then this is how you would integrate those diagrams. You drew your dipole-dipole, you drew your hydrogen bond diagram. This is actually, yeah, probably where I'd integrate them. Doesn't have to be a massive diagram, doesn't be crazy, but it just adds a little bit of detail.
Would we have to define the dispersion forces as well?
I wouldn't say so. I think that's fair to just quote it. You can just say that, yeah, I don't think you need to define it.
Okay, because there was one similar for my trials that they said we had to define dispersion, um, dipole, and hydrogen, where you have to talk about like the electrons creating the temporary dipoles due to the difference in electronegativity and stuff like that.
Was it a stem similar to this one? Just explain the order of boiling points.
It was they had, I don't know if you remember the CWSA 6 marker
I can pull it up.
this year. It was they had a table basically, and it was like explain the boiling points of specific, like the trended boiling points.
I've never defined it myself, but if that's what they're marking for, and you've been marked down for it before, then you could define it. In my opinion, it's not necessary, but again, risk mitigation, if you've been hit by it once, you just don't want to get hit by it again. So
Yeah.
may as well, if you know that's something you can lose marks for, and it applies for everyone as well. So if you wanted to, you can, but I've never seen it as a mainstay of these responses.
Yeah, I don't know. My response was basically perfect, but I lost like petty marks for
Yeah.
that.
Fair. Like 1 mark, 2 marks?
It was 2 marks.
I'd say this a bit rough. Anyway. Okay. So you know how organic acids and bases work. They function similar to an acid and base. This is not overly important. Same as this. This is extension. Yeah, I wouldn't say any of this is overly important. To summarize basically the whole thing, carboxylic acids are weakly acidic, amines are weakly basic, and everything else is pretty much neutral. These reactions we've talked about too, so that's the blue part in the flowchart. And esterification. Be familiar with the naming, properties, the actual reaction, which is a equilibrium. Everyone forgets this. Esterification is a reversible reaction, which can go backward and forward as the conditions of concentrated H2SO4 as well as heat under reflux. And the reaction itself involves an OH and H being removed from the 2 parts respectively to form a water and joining the molecules together as an ester. To explain the reaction conditions, you have to justify that the concentrated sulfuric acid is a catalyst. So the catalyst as well as a dehydrating agent, which removes water to shift equilibrium right. And it acts, and the heat under reflux acts as a source of heat, obviously, which increases rate of reaction. And the reflux acts to keep the reactants and products from being lost and hence maximizing your yield, as well as being a safety measure, preventing the buildup of pressure. 4 important safety considerations for esterification. Do not seal the top. make sure you use an electrical heating plate or hot water bath instead of a Bunsen burner. Using boiling chips to create a smoother boil, and of course PPE and cleaning up spills if they occur. Be able to discuss how you isolate an ester through the separating funnel, and quickly crash through those steps. You add distilled water to dissolve all the alcohol and carboxylic acid. That forms a aqueous layer. If you add NaHCO3 or Na2CO3, this can help you to neutralize any of the acid and potentially helps to increase purity as you do this process a little bit. Then you add that Na2CO3 treated mixture into the separating funnel, which forms an organic layer on top, which is the ester on its own, and a clear aqueous layer on the bottom, which has all of the alcohol, carboxylic acid, soluble salts, which you can filter out. So letting the stopcock open, you can filter out this whole aqueous layer, leaving just the organic layer inside the separating funnel. And you can repeat this process a few times to increase purity by taking out that organic layer, putting more water in, creating a new aqueous layer, and then filtering out anything else that was not already dissolved in the aqueous layer. So separating funnel. The other way is you can use a distillation process where if you have alcohol, carboxylic acid, and ester, ester should have the lowest boiling point. So if you know the boiling points, you would heat to just above the ester's boiling point in order to boil it out, condense it, and reform it as liquid in a separate sample. But be wary that you cannot use this if the boiling points aren't very different. Okay. Soaps and detergents. Be able to talk about what is a soap. Be able to draw a soap molecule with a carboxylate head. Be familiar with the terms hydrophobic and lipophilic. So the tail is both of those things, whereas the head is the opposite. It's hydrophilic because it has a carbonyl and a oxygen with a negative charge. So it forms ion dipole and hydrogen bonding with water. The soap mechanism. This is where you get asked most of your questions for soaps, although it's rarely come up in the HSC for some reason. The first part of using a soap is you obviously put it in water and it acts as a surfactant where when you put the soap in water, the polar heads will dissolve in the water and the non-polar tails will initially stick out of the water to not interact with it. So this occurs all over the surface of water and it breaks up the surface tension because now the water molecules at the surface are at an arm's length. They're not hydrogen bonded together. They're now broken apart and there's like a soap in between every single water molecule. So the surface tension of water is lower and allows water to actually penetrate as a cleaning agent better. Eventually, you'll saturate the entire surface with these surfactant molecules and they start to form micelles underwater, which puts the non-polar tails inwards in the middle. And there's no grease yet. This is just how soap interacts with water. You form these micelles, which allows soap to kind of just exist in water floating around in micelles too. So this is completely separate to what you talk about for the action on grease or a non-polar, something that's non-polar you need to clean. Where you write most of your responses is then below here. They ask you, explain the action of soap on grease, on oil, on fat, these non-polar substances. 4 stages, the formation of a bridge, where you have the non-polar alkyl tails sticking into the non-polar substance forming dispersion forces, and you have the polar heads forming ion dipole and hydrogen bonding dissolving in water. It is essential you state the intermolecular forces. That's what the markers are actually looking for. You have to then agitate in order to apply a mechanical action, lifts the grease up off the surface and allows more soap molecules to essentially get underneath the molecule as it's lifted up. I would just skip the incomplete micelle and just talk about this. Say eventually complete micelle formation occurs, where the droplets of grease are completely surrounded by soap molecules. And these micelles allow for the formation of an emulsion, which is when two normally immiscible liquids are made to mix. The micelles repel each other because there's negative charges around on all of the carboxylate heads, and this causes soap molecules themselves to repel and prevents them from reforming clumps. And so the suspended micelles can then be rinsed off by rinsing your plate or whatever you're cleaning. Any questions on the mechanism? Okay. You have a few limitations of soap. Can't use it in hard water because it makes scum, and in acidic solutions it also slightly decreases its effect, but it's not as important as the hard water limitation. Detergent is a synthetic compound that mimics the action of soap, where you have hydrophilic heads, hydrophilic tails as well, except the head can be either anionic, cationic, or non-ionic. The anionic detergents obviously have a negatively charged head. They are importantly still not as effective in hard water. And for cationic detergents, they are effective in hard water and they have a positively charged head. The only difference is that when they dissolve in water, the positive charge interacts with the negative dipole on water instead of the positive when you discuss the ion dipole being formed. And then lastly, non-ionic detergents, they don't have a charged head. They can be used in hard water because they just don't interact with the ions at all. And they form hydrogen bonding exclusively because they don't have a charge. Summary table. So I would recommend you take one case study for each one, where you have a example of a head that you can draw, and you should know a use linked to potentially its property and whether it works in hard water or not. This is a very high yield table. I would take this, screenshot it, memorize something like that if you haven't already. Don't worry about saponification. And this brings us on to inquiry question 6. So polymers, you need to know your 4 addition polymers: polyethylene, polyvinyl chloride, polystyrene, and polytetrafluoroethylene. Knowing addition polymers are simply molecules with a alkene that are attached one after the other and are repeating units one after the other. You don't strictly need to know the mechanism, but it helps with understanding how these polymers form. These are your 6 case studies. You need to know 2 variants of polyethylene, 2 variants of polystyrene, and then there's the polyvinyl chloride and polytetrafluoroethylene. So my advice here is remember how to draw the monomer, remember how to draw it as a polymer, and then be able to name a property linked to a use, at least 1 for each. If you can take 2 for each, even better. And these are all listed here. Finally, condensation polymers. You have nylon and polyester. So you should know these are polymers that form through a condensation reaction where you're combining monomers together, which either have a carboxylic acid, they either have a carboxylic acid and alcohol on either end. That allows you to do esterification and make a polyester, or they have an amine and a carboxylic acid, which allows you to make an amide over and over again, hence polyamide. To be clear, the cases you need for sure are nylon 6,6 and PET, or nylon 6, you can do either. Don't worry so much about protein, but you just need to have at the very least the syllabus provided cases. Once again, be able to draw the polymer, draw the monomers, which are a little bit harder, so spend a bit of time here. And once again, 1 property in use at least, if not 2. I would, of course, say take 2, but titrate down to how much you really want to put in this final week. Analytic 6, PET, and on the whole, polymers are less biodegradable if they have more CH bonds. And if they have more polar bonds like CCl and CO, they're generally less stable and easy to break down. Okay, so that's all for Mod 7. Any questions going back through any of that?
I have one.
Yep.
So, how do you name a cyclohaloalkane?
Good question. Let's draw one up. So let's say you have this starting simple. How do you name this?
1, 2, 3, 4, 5, 6. Is that 6 carbons?
Yep, 6 carbons. So
Um, will it be hexane? Cyclochlorohexane.
almost. It's a cyclo. The cyclo is going to stick together with the alkane. So it's a cyclohexane.
Mhm.
And then the chlorine, the halogen always comes at the front. So it's going to be chlorohexane. Sorry, chlorocyclohexane.
What if there are 2 halogens?
Yeah. So let's say there's now a second one. Let's say it's here.
Mhm.
Now you have to apply a locant because before we didn't need to. Wherever the chlorine was, it was just going to be number 1. Let's say the red one up here is carbon number 1. That means that the other chlorine is on carbon 3. This is now just going to be 1,3 dichlorocyclohexane.
Right. And say if there's a double bond.
Sure. If there's a double bond, let's say it's all the way over here, double bond there. Now it's going to be cyclohexene, and whatever that hexene is, it's going to be the lowest locant, since it is a higher priority than the chlorines. So it'd be hex 1-ene, and numbering to have the lowest point of difference for chlorine. Getting rid of these numbers. The lowest point of difference comes about if you number as 1, 2, 3, 4, 5, 6, because that would mean the first chlorine you name has 3, and then you have 5. Dichlorocyclohex 1-ene. But if you tried to number the other way, going 1, 2, 3, 4, the first chlorine would be 4. That's not as good.
Right. Can they ask if there is like say 2 double bonds?
Yeah, potentially. It'd be a rare case, but say they have a double bond here. This is now a diene. So it's 1, 3 diene, and everything stays the same in this case, otherwise.
Right.
Yeah.
Thank you.
All good. Any other questions? All right. Let's take a quick 5-minute break, come back and finish off Mod 8.
Let's look at
Alrighty. Okay. Start to come back. Got another module to work through. How are we feeling pace-wise and detail-wise, Josh, Ella? Good?
Yeah, good, thank you.
Okay, great.
What time do you reckon we'll be able to get through all of Mod 8 by?
I'll do my best, but I think 11:30 is probably
Okay.
the honest truth.
Okay.
So you need to head off before then. I know you got an exam.
Yeah, I might have to leave a little bit before.
Yeah, easy. And there will be a recording if you want to go back and check it later.
Okay, great.
Okay. Everyone else okay? Hunter? Lily? All good? Okay. So similar, stop me along the way if you have any questions. And actually, I forgot to do this for the last one, but can everyone type in chat the one or two things that they really want to go through and just get their head around again? Yep, AAS, definitely. Like the whole AAS, UV vis, colorimetry is where people, yep, AAS again, great. Splitting integration, yep, definitely. Yep, how the spectra actually work, how you make them, we'll definitely go through that. In as much detail as we can, permitting time. Answering 8.3 questions, yeah, definitely. So I think there's a recurring theme of wanting to go through some of the chemical synthesis responses. I think that's enough to get us started. Okay, cool. The things to focus on, AAS, structure for longer responses in chemical synthesis, and revisiting the spectra, IQ2 yield. Jay, do you mean more for IQ3 yield?
Yeah, that one.
Yep. Okay, cool. I'll just say yield. Okay, cool. Let's get started. Module 8, applying chemical ideas. So module split into 3 parts, and we'll start with the first. Okay. So you begin the module just introducing that the reason why we're doing all this is because we have to monitor how many ions or what ions are present in an environment. Know the common source of contamination are to waterways, soil, or atmosphere. You can have eutrophication of waterways. You can have bioaccumulation of heavy metals, and you can have disruption of pH in terms of acid and base being put in. So just know how to talk about each of those cases, what the consequence of each one is, and what ions or molecules would be specifically involved. Okay. Then you have all the qualitative ion testing. So this involves flame test, precipitation test, complexation tests for inorganic molecules. For organic molecules, that's all of your organic analysis, functional group reactivity, NMR, mass spec, IR spec. And then quantitative tests, which we'll get to in a second, are your gravimetric analysis, precipitation titration, colorimetry, UV-Vis, and AAS. So know what is qualitative and know what is quantitative makes it easier to group them in your head. Flame test, from applying heat to a metal, you are able to excite the electrons up to a high energy state. When they fall back down, they release that same energy as a wave, and you see that wave as a specific color. It's a different color for each metal, and you should be able to describe how you would do that method, as well as recognizing the common flames for these 8 ions, which are specified in the syllabus. For magnesium, I would add on, it's like a bright white. And I would also just add on lithium, sodium, potassium to this list as well to be really comprehensive. Precipitation tests, know your solubility rules. This will guide when things will and won't precipitate for like 99% of cases. And if you don't remember those, you can use a flowchart or you can reference this table. So you need to know what will and what won't form precipitate. You also need to know what colors will form if you do form precipitate. The most important ones would be your iodides being yellow with lead and silver, silver bromide being a cream color, sulfates all being white. Phosphates have a few variations, but you rarely precipitate with phosphate. Same with carbonate, because you often remove it as a first step with nitric acid. But hydroxide's colors, I would say all of these are extremely important. If you're going to go through a response and separate by hydroxide as your first step, you need to know what's going to be white, what's going to be something else. And that allows you to separate pretty much everything by just adding hydroxide. Okay. And then always, rule of thumb, if you don't know the precipitate color and you just don't know, just guess it's white. Most of the time you'll be correct. Complexation reaction tests. Complex consists of a central metal cation with ligands, which are molecules or ions around it, and they are bonded by a coordinate covalent bond, which consists of the ligand's electron pair being shared or donated, rather, to the central metal cation. The overall complex is going to have potentially has a charge, and you can find the charge by summing up the charges of all the ligands with the central cation's charge itself. You represent complexes within square brackets, and the charge lies in the top right corner. Question is really, why do we actually need these complexation tests? They're just another way that we can confirm the presence of a ion. In the case of copper, copper normally we can identify it by making a light blue precipitate when we precipitate it with hydroxide. But once you've made this light blue precipitate, you can prove that it's copper hydroxide once again by dissolving it in ammonia, because it forms a deep blue complex which is soluble. And that would look something like this. You have your copper in solution, you add some hydroxide or ammonia, which makes a light blue precipitate. And when you add excess ammonia to that solid, it redissolves and forms a dark blue solution, which consists of this copper ammonia complex. So just be aware that that's one thing you can do. Not so useful in copper because you can just do a flame test for the most part. But if they do ask it specifically, that's what you would cite. Same for silver. If you make silver chloride, normally we can just say you've made silver chloride, you can darken it in sunlight, that confirms. So usually that's enough on its own. But if they ask you for a specific case of how can we identify silver using complexation, then you have to state a case like this, where you say, I'm going to make silver chloride by precipitating silver with chloride ions. By adding NH3, this will form a soluble silver and ammonia complex, which will redissolve the solid that I formed. And you see the solution turn back to a clear solution from that redissolution process. The one that actually probably is important is the acetate ethanoate complexation, because you can't really precipitate acetate in any way, or any meaningful way anyway. So when you add iron chloride into acetate, what you'll find is that you produce a orange complex, iron with an acetate bonded to it. And if you were to add excess HCl that contains lots of chloride ions, you would be able to increase the chloride ion concentration, which causes equilibrium to shift right and removes that orange color. So the removal of that orange color is what you're looking for to confirm the presence of acetate in solution. And that's your acetate complexation reaction test. Any
Are
questions?
you expected to know the equations, or would you be given them?
I wouldn't expect the equations. Obviously, if you have them, it's a plus, but you should be able to analyze the things that happen as you go along. So
Okay.
the first step is you add iron chloride, which makes a red-brown solution, and you could just show the complex ion, and then you would say, because this forms an equilibrium with acetate and iron chloride, if I added excess HCl, this would remove the color, and it will remove the color by shifting the equilibrium right, and we would see a decolorization.
Right.
That would be the full explanation, but you could just simplify it to being, if I add iron chloride, the solution turns red, and if I add excess HCl after that, the solution decolorizes because the complex returns to its original acetate form, which is colorless. That would be a simplified version. Okay. So using all these qualitative tests, we can construct flowcharts which are able to systematically identify every metal cation and every anion by following the flowchart. Doesn't matter which flowchart you use, they all will get you there, but just whatever one you found is easiest to remember, basically just go with that one. These ones, I would say, are definitely on the more like rigorous side of things. They separate everything, and there's also a confirmation test at the end. So this is if you're going for high band 6 and you just really want every option, every base covered, you memorize this. The other options, the Chem in Focus one is actually quite good too. It provides a different sort of simpler way, but it doesn't have confirmation tests. And for anions, there's one below here as well. Okay. Cool. So that's all for qualitative. Spend some time on the flowcharts if they're not fully remembered yet, but I think by now the bones of them should be pretty much there. In organic quantitative analysis, you have your gravimetric and precipitation titrations. So gravimetric analysis basically just means analysis by mass. So you're determining constituents of a substance by analyzing the mass of what precipitates you form. There's just an example here you can go through, nothing too crazy, just from module 2. Whereas a precipitation titration, there's a few methods, Moore's method, and then the other two. I only have Moore's in these notes. Obviously, the other two can be assessed because they're pretty much just applications of titration. But the overall method of Moore's method, as the one that's easiest to understand, is that in solution, in your conical flask, and in your burette, in solution, you have chloride ions, and in the burette, you have silver ions of a known concentration. In your solution, you also have chromate ions, the CrO4 minus. CrO4 minus, or 2 minus. So as you add in silver, the silver ions will neutralize chloride bit by bit until all of the chloride is neutralized. That's the point where you've reached end point. Then you'll add in a little bit more silver in order to neutralize the chromate, not neutralize, to precipitate with the chloride and then precipitate with the chromate until you produce sufficient silver chromate solid that you see a color in solution that appears. So then the equivalence point is after you've added a little bit of volume to see that color change with the indicator. The source of titration error, therefore, is this difference between endpoint and equivalence point. You've had to add in a little bit more volume to reach equivalence point. That creates your titration error in a Moore's method titration. And in order to get rid of it, you would perform a similar titration, except you only have the indicator in solution, which means you add the same amount in order to see a color change. And by measuring the titration error through this way, you can take your, wait, hang on, sorry, I labeled these the wrong way around. The purple is the equivalence point, sorry. Purple is equivalence point, and green is endpoint. So then by measuring the amount that you have to add in to reach an appreciable color change, this whole amount is your titration error in a blank titration, adding this into just chromate ions. And so to find your equivalence point, you take endpoint minus the titration error. That's equal to your equivalence point. And you can address the error from a precipitation titration that way. Okay.
What was the color change for that titration?
Yeah, so the color change, believe it goes like a blood orange. Let me just verify that. Silver. It's like a brown red. Brown red.
So colorless to brown red.
Let me just check chromate as well. It's like a chromate itself is not colorless. Chromate itself is yellowy orange.
Oh, thank
So
you.
it goes from yellow orange to brown red, which is why it's kind of a bit harder to appreciate the color change. And you do need to account for titration error. Good question. Okay. You can also do conductometric precipitation titration. Similar to a normal conductometric titration, you have an equivalence point where the gradient changes. And this cuts out the titration error from the indicator-based method. Okay. Moving on to your quantitative analysis of colored species, we have colorimetry, UV-Vis, and AAS. I'll quickly go through each of them, and I'll spend a bit more time on AAS. To reintroduce everything, you have EMR. It exists on a spectrum, going from very short wavelength to very long wavelength. And for the most part, we're only looking at the visible spectrum for colorimetry. For UV-Vis, we're looking at UV and the visible spectrum, so a little bit more. And then for AAS, it's a mix of everything, but mostly visible as well. So we should know when we excite any atom element that is pushing electrons from a ground level up to an excited level. When it falls back down, it's going to emit a specific wavelength of light. And that can be measured in order to find out what atom we have quantitatively. For colorimetry, we see solutions as the complementary color of the light they absorb. So if the solution itself is blue, it will absorb orange light, or vice versa. The equation that we make significant use of is Beer-Lambert's law, which is absorbance is equal to log of intensity before transmission divided by intensity after transmission. And this is equal to epsilon times concentration times length, where epsilon is the molar absorptivity constant, concentration is C, and L is the length of the cuvette, which is typically 1 centimeter. It should also be noted that we have another measure called transmittance, which is different to absorbance. And transmittance is simply the intensity that was transmitted divided by the intensity that was initially shunned through. And you may also see that therefore absorbance is equal to the log of 1 on transmittance.
Can you please explain that again?
Yeah. The equation itself?
No, just the transmittance.
Oh yeah, sure. So to be clear, I naught is the light before it goes through the sample. IT is the light after it goes through the sample. Transmittance is therefore what percentage of light actually passed through. And to find that, you take IT on I naught is equal to transmittance. Because you may have shone through, let's say, 50 lumens and you got out 30 lumens. So the transmittance in that case would be 30 divided by 50 is 0.6 or 60% transmittance. Does that make sense?
Yes, thank you.
Great. Colorimetry as a method, therefore, you're making use of this complementary color absorbance and you're measuring how much light is going to pass through. You can either do this by constructing a calibration curve or by using Beer-Lambert law if you have the molar absorptivity constant for that substance already. The method itself involves looking at the solution, picking the complementary color as a filter so that you select that specific light. So here we've chosen orange. And before the filter, you're just shining through normal visible light in order to create a focused beam that goes through the cuvette. The intensity before and after will be measured, and you can measure it using a colorimetry machine. For our purposes, we can call it a detector. Steps are outlined again. Okay. So if you're going to use the calibration curve method, you start by taking standard solutions of known concentration, and you measure each of their absorbance in order to construct a curve, where if it's 0, 0.002, you essentially can plot all the absorbances versus concentration. This allows you to create a curve, and then if you have any new solutions of unknown concentration, such as one that maybe measures here, you can interpolate on your graph to find what the concentration of that solution actually is. Okay, and alternatively, you can use Beer-Lambert law. So if you have the intensities, you have the molar extinction coefficient, which is epsilon, then you'll be able to solve for absorbance, you'll be able to solve for absorbance using the intensities. And then because you know the length as well of the cuvette, 2 centimeters, taking the absorbance, the length, and epsilon, oh, wrong way, absorbance, length, and epsilon, you can compute those to find your concentration using Beer-Lambert law. So typically they're what you're solving for, and absorbance may require you to solve intensity naught and intensity transmitted in order to get to absorbance first. Typically, this is the flow of every response you do for Beer-Lambert law with A equals ELC. Okay. UV vis. UV vis is slightly different, where you extend the method to the UV spectrum, and it's not you don't select your wavelength based on color. You select it based on a readout, which allows you to find what wavelength absorbs light the most, or what wavelength is absorbed the most by this sample. You still use the same method of a calibration curve or the molar absorptivity constant because you still have a cuvette. But the main differences are you include the UV spectrum from the use of a deuterium lamp. You use a monochromator to select wavelength instead of a colored filter. And there's no concept of this complementary color stuff from colorimetry. You choose the correct wavelength by doing a full spectrum scan, something like this, where you scan the absorbance of a sample at every wavelength in the UV and visible range from about 190 nanometers to 700 and something. So taking a scan like this allows you to see at the low wavelengths, it doesn't really absorb much. Towards the middle, it does. And then at the very end, there's not really much absorbance there. So the best wavelength to choose is one of the wavelengths where you have significant absorbance, such as this or this. They would be the best to choose because you want the highest absorbance as the wavelength you shine through your sample. And that's pretty much the main differences. The only other difference, you can do this in colorimetry too, is if you compare against a reference sample, the reference sample will allow you to control for any absorbance that occurs because of the cuvette or because of just water alone. And if you compare this as your I naught and this as your IT, it gives you a slightly more accurate measure of absorbance because now it's only really accounting for the sample. So the I naught would be here, the IT would be here. Okay. Important to note, well, somewhat important, not really high yield. For UV vis, you can also use this qualitatively to identify chromophores, which are bonds that absorb specific wavelengths of light. So it's sort of similar to a IR spec almost when you see these, but you can see carbon to hydrogen, carbon to carbon, carbon to carbon double and triple bonds, and carbon, chlorine, carbon to bromine. You can see those as specific wavelengths if you were to shine this through a sample that contains them. They would be absorbed at those specific wavelengths listed, and this is on your data sheet. So it's never been assessed, but it is there. So I would hedge my bets and just be confident on at least knowing this is where the information links to. And all of this enrichment stuff is not necessary. I'm going to get rid of it. Okay. Important case where you have overlapping samples. So they're saying you have two samples in the same solution, you mix them together. If you're selecting the best wavelength to analyze solution B, you're going to want to choose the one where there is least interference with A. So it wouldn't make sense for B to pick, for example, here. That's not sensible. You want to pick the wavelength where there's very little interaction with A. So something like 700 or 700, probably 700 makes the most sense as the peak wavelength, and there's very minimal interference with A already. And these are your chromophore graphs where you do see that on the y-axis it's transmittance and on the x-axis is wavelength, and you'll be able to correlate each of these troughs with a specific chromophore or several troughs with a specific chromophore. Okay, AAS. Let's really get into this. Can someone try to tell me what the difference between, like, what's the key difference in AAS with the other two methods we've just looked at? Any key differences?
The source of light.
Source of light. So how's it different?
In AAS, you use specifically incandescent lamp, which is made from the metal you're looking for.
Right? And
Concentration.
so when you shine that metal's light out, importantly, as Aaron's saying, the light is originating from essentially an excited gaseous metal sample. So it may be a calcium lamp, for example, is shining out the specific emission spectra of calcium. So you would have calcium in here in the case where you're trying to analyze a solution that contains calcium. So whatever you're trying to analyze, you need to use a lamp that correlates to that metal. So calcium would shine out its specific spectra. Let's say it shines out a blue light, shines out a red light. Actually, we know calcium shines out a red light because it's brick red. And let's just say it shines out some light in a let's say it does one more color, let's say it does green and something else outside the visible spec. It would shine out the specific wavelengths that correlate to its transitions. So it may only be 3 wavelengths that come out, hypothetically, but it's 3 specific wavelengths that are specific to calcium only. So then what you would do with calcium in solution, because you're trying to analyze what's the concentration in here, you would take up solution of the calcium and put it through an atomizer, and it turns it into atomized calcium within the flame. Which of those 3 wavelengths of light will this calcium in the flame absorb? Which of those 3?
Is that all of them?
All of them, because the wavelengths that calcium emits match exactly the wavelengths that calcium would absorb. And this is the power of AAS. The wavelengths that you put through the sample specifically select the metal that you are trying to analyze, which is why we match the metal in the cathode lamp with the metal in solution. Does that make sense for everyone? Any questions there so far? Okay. So that would mean that each of these wavelengths is absorbed to some extent, like so. And they go into a monochromator. The monochromator selects one of the wavelengths. You can select any of the 3, but if you were to do it to the best practice, you select the one that is absorbed the most. But let's just say you selected the red one because we know calcium is a red light. Actually, hang on, you would still have these. The monochromator, let's say you went through and you selected only for the red light, and now you analyze only the absorbance of that red light after the monochromator. Can you use A equals ELC here? Should be very firmly saying no. We cannot use A equals ELC because we don't have any length. We don't have a cuvette anymore. So AAS, you can only use calibration curves to analyze. You cannot use A equals ELC. So for the rest of AAS, you're essentially testing standard solutions of calcium, finding what their absorbances are by measuring after the monochromator, and constructing a calibration curve to test any unknown concentration of solution. And that's pretty much it on AAS. Obviously, there are some advantages and disadvantages to each of these methods. Are there any questions going back through AAS?
Just quickly,
Yes.
when you put, like, when you're saying you're putting the calcium into like the nebulizer thing,
Yeah.
what does that mean?
Yeah. So when we say we atomize the metal, it's turning the ionic form into its atomic form. And it's doing that by taking up a solution of calcium. So you have your calcium solution, it goes into the flame at a constant stream. And that calcium solution is being like heated to the point where the water evaporates and the calcium returns to its solid form, or its neutral form, and it can become its gaseous state if it's hot enough. But the point is the calcium is neutral and it reflects the transitions of a neutral calcium atom.
Right, okay. Thank you.
Okay, cool. Any other questions?
Yeah, so when the calcium gets heated, like does its electron like not get excited because of the heat?
It's a good question. I'd imagine it does, but the idea is that even if the calcium was heated in the flame, and yes, it would be, excites and falls back down, and it may like spray in different directions. We're only looking at 3 concentrated beams of light, or like 1 concentrated beam of light, and how that beam changes. And some of the calcium may not be excited yet. So we're looking at how much of that light gets absorbed from this specific beam, and it might trickle down to be a little bit less as we see here. But yeah, I do agree. Calcium would probably also be excited from the flame itself.
So why does it not affect the results?
It wouldn't affect the results as significantly because all of those wavelengths of light from calcium would splay out in 360 degrees in 3 axes. So the light is being like dispersed, whereas we're only analyzing a focused beam.
Right.
So calcium would spray out light this way, this way, this way, this way, this way, this way, and out of the page and back into the page. Sure, some of it may go into the monochromator as well, but only like this one beam is going to go in out of infinite directions around. So the dispersion of the light means it's not that significant, but yes, it would be some form of inaccuracy maybe. We're looking at a very concentrated beam that goes straight through the flame like this and is all going in the monochromator.
Right. So
And
can you write this? Can you write this thing as a limitation?
I would search it, but it makes sense to me what you're thinking. I don't think it's going to come up as something you need to write though. I don't think it's the biggest limitation. The limitations are that you need to know what metal it is before you do AAS. You need a unique lamp for each experiment, which can be expensive, and the calibration takes a bit of time to occur. So it's a bit less effective if you need something that's very rapid and quick. But if you have a lot of samples to test over time, once you've done the calibration, it's very quick to test concentrations.
Thank you.
Okay, cool. Summary table. I really like this table. It really helps you to see what the differences are in terms of light source, how the sample enters, what samples you can analyze, qualitative, quantitative, and the role of the monochromator, I guess, is somewhat important too. So the AAS, the only other difference is the monochromator comes after the absorbance. Okay. Organic analysis. You have your reactivity tests, carbon-carbon double bonds, hydroxyl groups, carboxylic acids. Basically for your double bonds, bromine water and bromine water test. If it's saturated, it'll decolorize. If it's unsaturated, it won't. Make sure you do it in a dark room though, because an alkane in sunlight will still decolorize. Hydroxyl, you have your sodium test to identify any alcohol, but it will show the same result for primary, secondary, tertiary, so it doesn't separate them well. Esterification allows you to see if there's an alcohol as well, but it's not a great test because a lot of things smell. Oxidation allows you to separate primary and secondary from tertiary, and you're looking at the color change, whether it does change or whether it doesn't. You should always acknowledge that if you don't know your substance is an alcohol for sure, and you have a negative result from an oxidation test, it may still be something that is not an alcohol. So if you want to be sure, when you get a no visible reaction from an alcohol being oxidized, that you do a sodium test to confirm whether it's a tertiary alcohol or actually something else. Lucas reagent allows you to separate primary, secondary, and tertiary alcohol based on the formation of a turbid layer over time and how quickly that turbid layer forms. For a primary alcohol, you have no visible reaction. Secondary alcohol, you have a reaction over 5 to 60 minutes, which turns cloudy, and for tertiary alcohol, you have an immediate reaction. The actual thing that you're forming is an insoluble alkyl halide, which forms when you remove the hydrogen bond forming OH and replace it with a chloride on the alcohol.
I have a question. So
Yes.
for like confirmation test of alcohol, can you just use Lucas reagent?
But what do you mean by confirmation test?
Like, do you don't know if it's the substance is an alcohol or not?
Right. I would. Well, you would miss the primary alcohol, so I wouldn't use Lucas reagent to confirm the presence of an alcohol. I would use the sodium test, keeping in mind that it can give false positives with a carb acid or with water. So you need to have a dehydrating agent when you use it, like calcium chloride, to be really thorough. So I would use sodium test to confirm the presence of an alcohol, but being aware that there are false positives that can come about.
Right. Thank you.
Lastly, carboxylic acids. You can identify these with a pH test or with a reaction with metal carbonate to make CO2 gas, and you can confirm this with a lime water test. Okay, this question's really good. If you can do this, then you can do all of the functional group testing. All right, organic analysis. So we have IR spec first, and the way I'll structure this is I'll talk through the method, how it works, just to revise that, and then we'll just talk quickly on how you read the spectra. IR spec comes from shining infrared light through a sample and exciting the vibrational energy level to a higher level than it began with. Then the absorbance of that IR radiation can be measured on a spectrum, and depending on which wave numbers have the highest absorbance, you can tell what functional groups you have or what bonding groups you have, since different bonds will vibrate at different energy levels and transition with different amounts of energy. So the way that IR spec actually works is you will transmit IR light through two solutions, blank and the sample. You measure the intensity of each one in order to find the transmittance. And the transmittance is going to be therefore your y-axis. By plotting the transmittance over all the different wave numbers from 4,000 down to 500, you form an IR spec, and based on the features you find on that, you can measure what function groups you have. To interpret, make sure you always write when you describe a trough, you have to talk about what wave number it is, how deep it is, and what the breadth is. You can do that in just one sentence very efficiently. And you're always looking for regions that have either high transmittance where you're normally expecting troughs in order to rule out bonds that you don't have, or you're looking at regions that have low transmittance to find out what bonds you actually do have. So you can talk about both. You can say this region has no trough, therefore we don't have blah. Or you can say this region has this broad, deep trough at 3,000 indicates that we have a OH hydroxyl from an alcohol, something like that. The fingerprint region, whilst we don't really use it for most of our analysis, and it can help to identify molecules with a computer and their database, we still can get information from it, particularly the 1,000 to 1,300 range for the C single bond O. That's important for your esters, alcohols, carboxylic acids, just as an extra piece of information, but particularly for esters. So always note that as a possibility if you have a deep, narrow trough around 1 to 1,003. And then your broad troughs at high wave number be able to separate alcohol from acid from amine, and features that you look for are here. So pros and cons listed here as well. And that's all on IR spec. Any questions going back over IR spec? Okay, mass spec. So you have background understanding from physics, F equals ma, and understanding that first, an electric field is going to accelerate particles that are charged, and they will go towards the opposite charge. So if you have a positive particle, it's going to be accelerated towards the negative charged plate. And that molecule or that ion will therefore over time gain velocity because it's being accelerated. Secondly, charged particles with velocity will enter centripetal motion in a magnetic field if they enter at a perpendicular angle. And that means that charged particles such as what we're going to be using in mass spec, the positively charged particles, will be bent and deflected. And based on how heavy they are, they'll either be deflected more or less. So if you have a particle that is lighter, it will deflect at a sharper angle, or it will deflect more. And if you have a heavier particle, it will deflect relatively less. So then mass spec, as a whole process, starts by injecting an organic sample in, bombarding it with electrons in order to break it into fragments, charged fragments, which are pieces of the molecule with a positive charge of 1+. You then have an electric field, which you put those charged particles into, and it accelerates those particles towards the negative plate. Once they exit from that negative plate, they go through a magnetic field, which deflects the heavier particles less and the lighter particles more. And by scanning this whole spectrum over a detector, you can find what fragments occur at what level of abundance. So if there's more of it, there'll be higher abundance, and if there's less of it, you would have less abundance. And you're essentially plotting on a scale, you would be plotting the mass to charge ratio as your x-axis and the relative intensity or the abundance as your y. Important peaks are your base peak, which is the most abundant fragment, as well as your molecular ion peak, because that tells you your molecular mass. And then each of these peaks below, the smaller ones, these all still represent a possible fragment of the molecule, and you should be able to identify the fragment based on what signals you see. Important features to not miss otherwise. There's some common fragments that help if you do have the common numbers in your head just as like reference. And the isotopes. Do not mistake the molecular ion with any of the isotopes that can possibly form. So if you see a big molecular ion looking peak and then a small one next to it a little bit higher, +1, do not take the little peak as your molecular ion. That is your isotope. Chlorine, 3-to-1 ratio. 3-to-1 ratio, where the smaller one is a molecular ion and the top one is the isotope of chlorine 37. And then for bromine, you have 1-to-1 ratio, where the bottom one is a molecular ion and the one above is again an isotope, but this time of bromine. So these are your 2 important cases to recognize as well. 3 important cases. Advantages, disadvantages, and that's pretty much all for mass spec. Okay, any questions on mass spec? All right. NMR, proton NMR, carbon NMR. Be able to talk about how the NMR spectra actually forms. So you need to know that Spin is a property of nuclei with an odd number of protons or neutrons, and that generates a magnetic dipole. So 13 carbon and a proton both have an odd number of protons and neutrons. The actual process of creating the NMR spectra involves firstly having nuclei that have non-zero spin, such as a carbon-13 nuclei. They are normally haphazardly arranged, and then when you apply a magnetic field through them, they all snap in line, either in a parallel orientation, where they're in the same direction with their dipole with the magnetic field, or they're anti-parallel, where they are against the magnetic field but in the opposite direction. Anti-parallel means that the molecules are at a higher energy state, and you can transition you can transition nuclei, not molecules. You can transition nuclei from parallel to anti-parallel by applying just the right amount of energy. When they fall back down from anti-parallel to parallel, they emit energy, and that's what is measured in a NMR. And you form signals based on the number of carbon or hydrogen environments, how chemically shifted they are, and some extra features appear in a HNMR. Know how to identify chemical environments? So an identical chemical environment means that all of the stuff bonded to that carbon, so this blue carbon has 3 hydrogens and it has a CHOH as well as a CH3. It has these 2 pieces bonded, or these 4 pieces bonded to it. If something is to be an identical carbon environment to that blue carbon, it has to have exactly 3 carbons, sorry, has to have exactly 3 hydrogens and a CHOH CH3 bonded to it. And that's what you would see on this far right carbon. It has 3 hydrogens, 1, 2, 3, and exactly a CHOH CH3 bonded to it. So it's not just about what's adjacent, it's about the arrangement of everything that's adjacent. Okay. So we've talked about the environments, and environments are important because they tell us how many signals we expect to see. But the signals can occur either very far to the left or very far to the right on your spectrum, and they're compared against what we call TMS. TMS is tetramethylsilane, which is one of the most shielded molecules and acts as our control. A carbon or hydrogen region will appear further to the left if it is more deshielded. And deshielding comes about when you have an electronegative element that it is in close proximity to that carbon or hydrogen environment. So this carbon environment is very close to an oxygen, which means that its electron density will be drawn away, meaning this carbon is going to be severely deshielded. That means the energy difference between parallel and anti-parallel is bigger, and you'll have a bigger chemical shift because of more energy required to move it. So the signal goes further downfield, and this is why the most deshielded signal furthest to the left here is the carbon bonded to the carbonyl. Compare that to the others. B is the next most deshielded because it is still in relatively close proximity to the oxygen, but it's a little bit further away. And then lastly, A is the most shielded because it has pretty much no electronegative elements nearby. And your chemical shift data is all given in the data sheet. So you should be comparing your signals ppm number on its x-axis against the ranges to identify what specific bonds or groups that you have. And be specific. Okay. So for CNMR, we talked through how you need to talk about the regions and you need to talk about the shift. That's it, really. But for HNMR, you have to do regions And typically, you don't actually talk too much about shift, but if you wanted to, you could. Shift, if they give you the data, so I'll put in brackets. 3, you talk about splitting. And 4, you talk about integration. So this is for carbon. 13, this is for proton. It's a bit of a longer list. So similarly, the number of hydrogen regions reflects how many regions you have, or how many signals you have. And then the shift is the same. If you have electronegative groups nearby, you expect the hydrogen region to be further to the left, but there's a lot more exceptions here. What is always black and white is splitting and integration. So splitting occurs because of spin-spin coupling, which is due to the interactions between neighboring hydrogen atoms on adjacent carbons. And the splitting pattern follows the n+1 rule, where n is the number of hydrogens attached to all next door neighboring carbon atoms. And then the 1 is just added onto that to find the number of splits. So you can have singlets, doublets, triplets, quartets, quintets, so on. And taking as an example, just again, CH3 over here, actually let's do CH2, region B. You can see that on the neighboring carbon environments, so this carbon and this carbon, there is a total of 3 hydrogens, 3 on the right one, 0 on the left. Therefore, because there's 3 hydrogens on neighboring carbon environments, there should be 3 + 1 signals, hence a quartet in this case. Finally, integration is a ratio between the number of hydrogens in each region. So if you have 3 hydrogens versus 2 hydrogens versus 1 hydrogen in each region, the ratio of the integration should be 3 to 2 to 1. And integration is just that, it's a ratio. And this is the shift data that you may get given in your exam for HNMR. It's not in your data sheet, but it can still be given. So to summarize all that, when you actually go about writing your organic spectral analysis responses, structure your response, be very specific, describe everything that you could possibly imagine you need to describe. If they give you a spectra, you must talk about it. Even if you don't need it to arrive at your conclusion, you have to talk about the features. Don't be afraid of extra writing paper, although you need to clearly label when you do use it. And at the end or start, always, 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 if it's an identify the molecule question, place a name and drawing of the molecule at the start or end. Okay. Any final questions on organic spectral analysis? Okay. The final thing we'll talk on is chemical synthesis responses. And I think we had a few requests. So what specifically did you want to learn more on for these responses? For those who said they wanted to go through chemical synthesis, just to help me answer better.
Just like with when it has like the diagram of like a synthesis per se, I don't know, like
Yep.
ammonia or something, and it's like listing what is like beneficial in the synthesis like diagram. I feel like structuring a response to that and like making sure you get everything in that question.
Yeah, sure.
Yeah, basically the same.
Same thing. Okay, great. So essentially, it's not too difficult to structure those responses, but when you see something like this, a question where they give you a whole setup and there's all these features going on, they say explain X number of factors and how it has been considered to optimize production, or suggest a way in which you could improve this method to optimize production. The structure would basically just be 1, identify whatever you're talking about very clearly. So say, for example, we're using a heater. Let's make it simpler. We're using a catalyst bed of iron oxide and potassium oxide, right? So you'd identify what you're talking about. Two, you would talk about its effect. Explain effect. So if it's a catalyst bed, you're going to explain, therefore, that we're using a catalyst bed because it provides an alternate pathway with a lower activation energy, which means that success rate of collisions is higher, and therefore rate of reaction is higher. This means that our reaction proceeds at a faster rate with no change to the yield. And when you explain the effect for these questions, it's best practice to either link it to rate of reaction or effect on yield. So you explain how it does it, and you explain what effect on rate or yield it has. And it could be both. Does that make sense in terms of a structure to follow? Okay, so I'll follow that. And just being very clear on differences on effect of rate and yield. Don't conflate them together because they're often different things. Okay, but going back up to the top, throughout this last dot point, you're essentially just talking through the differences in rate of reaction, yield, and sometimes purity from any chemical synthesis process. To be very clear, rate of reaction, how fast the reaction proceeds, yield, how much product you make, where you can have theoretical versus actual yield. Theoretical is the amount that you should make, actual yield is how much you actually do make. Purity, lastly, is the proportion of product which is actually the product you want. And in any chemical synthesis process, if you're given the delta H and you're given the equation, you should be able to talk about the effect of changing reaction conditions, such as pressure, volume, concentration, and temperature, as well as the effect of adding a catalyst. If you change pressure or volume, you're always trying to increase pressure, pretty much, to as high as possible without going to an extreme pressure, because in synthesis, you're typically combining more moles into less moles. So that would not only increase rate of reaction from having a higher frequency of collisions, it would also increase yield because the reaction will want to shift to the right to decrease pressure. Concentration is also fairly black and white. If you're increasing the concentration of reactants, you are not only increasing rate of reaction because of more frequent collisions, you're also increasing the yield because you simply have more reactant to make into product. Temperature is where there's a bit more debate, where you may have what we refer to as compromise conditions. So it has two streams. If you have delta H, which is less than 0, or delta H that is greater than 0, the easier of the two is where you have delta H greater than 0. This will increase rate of reaction because you increase success rate and frequency of collisions. And it will also increase yield because it will shift forward in the endothermic direction in order to bring back down the temperature. The hardest case, which is still not too bad, is if you have an exothermic reaction. Yes, this will increase rate of reaction if you increase temperature, and I'm talking about everything in terms of increase in temperature, increase in concentration, to be clear. If you increase the temperature and you have an exothermic reaction, you will actually decrease the yield because the reaction will shift left in order to bring back down the temperature. So this is where we want to apply compromise conditions and select a moderate or moderately high temperature. And lastly, with a catalyst, it increases your rate of reaction, no effect on yield. So be clear on those 4 cases. That's all the changes they can ask you on mod 8. Genuinely, that's like all the cases. So if you have those under your belt, you should be able to talk about any effect on rate or yield and any optimizations of rate or yield in isolation or together if you need to. Keep in mind there is a dot point about examples of chemical synthesis in pharma, cleaning products and fuels. Just given some here, but this rarely ever comes up. Environmental, economic, and social considerations, a few here as well, just of chemical synthesis and design. And that wraps up module 8. So if there are any questions, actually I'll just ask first, are there any questions? Module 8, going back through anything?
Yeah, I just had a question about like answering the like identifying like anions and cations.
Yeah.
Like when you write an equation for it,
Mm.
like let's say you had carbonate ions and you like use nitric acid to like make CO2 bubble.
Mhm.
When you write out the equation, do you react CO2 with HNO3?
Mhm.
Do you write the like on the other side, do you write the like nitrate spectator ion or not?
I would I mean, if you're only going to be reacting the carbonate, like yeah, you can. I don't think
Yeah.
it wouldn't be wrong unless they asked you specifically for a net ionic equation. But yeah, I think it's fine. You can include the nitrate because usually you will have the like metal
Yeah, you'd have
cation.
like sodium carbonate or something. Yeah.
Yeah. So I would just include it. I think that's
Okay.
fine.
Yeah. All right.
Okay. Any other questions?
Can we go over overlapping and IR spec?
Overlapping as in for the broad troughs, you mean?
Oh, yes.
Yeah. So all that means is when you have a broad trough such as alcohol, carboxylic acids, hydroxyl, or the amine, alcohol and amine will not overlap with the CH trough that exists around, I think it's usually like 2,900-ish. But because a carboxylic acid exists in the range of 2,005 to 3,000, it oftentimes will actually overlap with that CH, which is usually here, but you can't see it because it's been overlapped. Does that make sense?
Oh, yep.
Okay, cool.
And the other one is, can you please go to mass spec?
Yep. And the question is?
Can you get that the actual that one, the diagram?
Yeah.
So the value for the charge to mass ratio which you get is detected by the detector at the end.
Yes.
Right. Yeah, that's it.
Okay, cool.
Thank you.
Well, I mean, actually, I think there's some way of doing the maths, and the mass spec process does that for you. The detector detects the abundance. Not so, it doesn't tell you the mass per charge.
Oh, so it just tells which, no, so it just tells, it should, because it tells which mass to charge ratio, I mean, which fragment is the highest.
Yes. It'll tell you how much of each mass per charge you have. So it tells you how much of that ion you have based on how often it's being hit by that ion. But the mass per charge, I think you actually find it out from doing the maths of physics, and you can't know that unless you do physics.
Right. Thank you.
Okay. Any other questions? Ella, Jay?
What'd you say?
Oh, any questions?
Oh, no.
Okay. Cool. Well, then we'll probably leave it there, right on 11:30. There'll be a co-working session today, starting from about, I think I might actually start it from 12:30. So if you want to hop on and just study together, and have some accountability throughout the rest of the day, more than welcome to. And I'll be on the call from about 12:30 as well, just answering any questions if they come up for you guys. if you have to study something else, more than welcome to come along as well. You don't have to have your camera on. Just if you want to be seeing other people studying with you, I don't know, maybe it's motivation, but up to you guys. I'll be here, and you can treat it as a drop-in session otherwise. So I'll leave it there.
Yeah.
Have an enjoyable rest of your day. And if I don't see you before the weekend, then best of luck for your exams later in this week.
Thank you.
Thank
Okay,
you.
thank you.
Thank you.
Thanks, Jeff.
No worries.